morning, everybody. Today I'm going to talk about the nanoscale and macroscale synthesis of mixed metal oxides. Basically, I will focus the presentation in a vanadium phosphorus oxide system. First of all, why it's important to study these systems? Well, basically mixed metal oxides possess very interesting properties, catalytic properties for the oxidation of lower alkanes. Two clear examples of that are the system molybdenum, vanadium, niobium, and antimony vanadium oxides for the oxidation of ethane and oxidation of propane. The other well-known system is the vanadium phosphorus oxide in the oxidation of N-butane to maleic anhydride. The big challenge is that nowadays the conventional synthesis methods for these mixed metal oxides offer very limited control over the structural and compositional properties such as bulk and surface composition, formation of desirable active catalytic phase, preferential exposures to very specific surface planes, also surface areas, and pore architectures. So, in other words, there is a critical need to develop new synthetic methods for the synthesis of these novel mixed metal oxides for applications in catalysis. Macro and nanoscale templated synthesis of nanocrystalline mixed metal oxides represents a very interesting and an attractive approach for the design, hierarchical design of these new materials. Several macro and nanoporous single components has been synthesized in the past, and these materials have shown very interesting properties, very interesting surface compositions. Let me show you some example of what I'm talking about. This is a picture of MACROPOROUS titania single oxide showing these beautiful ordered arrays of pores showing very high surface areas. This was synthesized by Andreas Stein. Talking about the other approach, nanoporous approach, the best example is a well-known system, MCM41 type materials. Again, we have these cylindrical ordered cylindrical pores, but now we have it in the nanoscale. So these are two examples of what has been done with this type of materials, with the approaches that I'm talking about. So the motivation of this work is that the single component oxides have been synthesized, but not mixed metal oxides. And well, the idea is to develop the hierarchical design of these materials and try to apply in the area of heterogeneous catalysis. So basically, this is the focus of this presentation, the hierarchical design of these materials using these two self-assembly routes. We will demonstrate in this speech that it's possible to improve or to have control over the desirable properties that I talked at the very beginning of this presentation, talking about the bulk and surface composition, desirable catalytic phase, preferential exposure of active and selective surface planes, to control surface area somehow, and to end with materials with very nice pore architectures. First of all, I'm going to talk about the first proposed mechanism, the macro templated approach, design of macroporous mixed metal oxides, basically focus on the VPO system. The idea here is that we're going to use as template colloidal arrays of polyestyrene spheres with known size. The idea is to permeate our inorganic precursor, VPO precursor, between the voids of these spheres. The precursor will condensate in a very nice framework, inorganic framework, and then the idea is to remove the template using calcination burning the spheres or using selective solvent extraction to end with this macroporous VPO materials. Let me show you the spheres, the template that we are using for this synthesis. We have synthesized these spheres using the emulsion polymerization process. This is, as you can see, very monodisperse colloidal spheres. Obviously, we can manipulate the size of the spheres. Then the idea is to form this colloidal array of spheres. This is done simply by centrifugation or sedimentation. The proposed mechanism for the formation of this material self-assembly of our VPO around the spheres, it's quite simple. The idea is that our spheres doesn't have at all chemical functionality in the surface. So the idea is to use any phosphorus source, basically phosphorus acid, to phosphate the surface of the spheres. Then our vanadium species will condensate basically around these phosphated spheres, and we end with our asynthesized material. Let me show you what we have done so far in this work. Show you the self-assembly of the polyestyrene spheres with our vanadium phosphorus oxide precursors. So we end with fresh MACROPOROUS. It's a compound of spheres and inorganic framework. Then we remove the spheres using calcination or subfluid extraction. We end with these materials MACROPOROUS, and then we proceed to do the characterization using, determination of surface areas, the inspection of morphology, determination of crystallographic phases, and chemical analysis. This picture shows basically the asynthesized material. So you can see here we have our array of spheres, and the inorganic precursor, inorganic VPO, is condensing around the spheres. After template removal, we end with these highly, or at least ordered, macroporous VPO materials. The pores of these materials are the ones that were occupied at the very beginning for our spheres. So the walls are composed by different VPO phases. In this case, we're talking about cavities of the order of 0.4 microns, which is more or less the size of the spheres that we are using. And you can see here interconnected pores of 0.2 micron diameter. Other beautiful characteristics that we can achieve with this proposed method is surface areas. I'm showing here that using the conventional synthesis methods, we end with VPO phases with surface areas in the range of 5 to 20 square meter per gram. With our proposed self-assembly route, we are talking about 40 to 75 square meter per gram. So we are improving somehow surface area of materials. Another very interesting feature of this proposed route is that by choosing the appropriate VPO precursors, we can end with different crystallographic phases. Of course, for the special case of this system, we are trying to have vanadium pyrophosphate, which is the active and selective phase for the oxidation of N-butane. However, using different vanadium sources, phosphorus sources, we can have different crystallographic phases. Another important characteristic talking about the reaction of N-butane oxidation to maleic anhydride is the preferential exposure of the most active surface planes, that is 100. It has been proposed by many experts in this field that this plane 100 is the most selective and active for the transformation of N-butane to maleic anhydride. So basically what I'm showing you here, these three XRD patterns are for conventional VPO methods, synthesis of VPO, conventional VPOs, phosphide route, aqueous route, organic route. As you can see, these ratios of preferential exposure of the desirable plane are very low compared to our macro VPO. So let me summarize here what I have talked about with respect of macro VPO approach. We have obtained materials with desirable pore architectures and pore system, VPO phases with very high surface area. I mean, high surface area compared with conventional VPOs. Optimal bulk compositions, talking about PV ratios of around 1, which is it has been shown that these values needed for higher catalytic performance. We have obtained the active catalytic and the active phase vinyl pyrophosphate for the oxidation of butane, and also the preferential exposure of the selective and active catalytic planes. Now I will talk about the other approach that we are using to obtain these novel materials. First of all, let me talk about the mechanistic aspects for the formation of mesoporous materials. The well-known MCM41 materials proposed almost 9 years ago. The idea here is that we have a template or surfactant that in presence of aqueous solution forms micellar roads. Then under very specific synthesis conditions, these micellar roads associates themselves to form these hexagonal arrays. Then the silicates permeates or condensates around these micelles. After that, we remove the template and end with these cylindrical nanoporous structures. In our case, this is the originally proposed mechanism, but there are some alternatives that we can use for the formation of nanoporous VPO. The first approach is the one I showed. It's an anionic approach, basically charge matching between a positive charge surface of our surfactant and the negatively charged species of our inorganic framework. The other approach is a non-anionic approach. Here it's proposed that we have neutral templating of our neutral template with neutral inorganic species. Basically, the driving force for this assembly has to do with hydrogen bonding. Talking about the first approach, anionic approach, this is basically what's the general picture of the self-assembly of our VPO materials. We have our surfactant, presence of water, forms these micelles. We are using here cationic surfactants, so the surface of our micelles will be positively charged. Then our phosphorus source, by simply charge matching, will condensate around or will attach around these positively charged micelles. And finally, our vanadium species will condensate around the layer of phosphorus source. In the other approach, we have the non-anionic self-assembly. Basically, as I said before, here the idea is that the driving force mainly is hydrogen bonding between neutral surfactant and neutral VPO species. Now, the idea is to have this neutral VPO species. So basically, to do that, we have to work at the near regions near to the isoelectric point. By definition, this is the pH at which the surface of an oxide has an overall charge equal to 0 in suspension. So near the isoelectric point, we can have neutral VPO species, so that allow us to have this self-assembly. And basically, we have learned that when we work in this region, we get much more stable nanoporous VPO materials, since, well, near the isoelectric point, the inorganic species will tend to agglomerate and cover all the micelles, and also the condensation rate is slow enough that will allow our inorganic species to condensate around the micelles. Again, in a similar fashion, for the synthesis and characterization of nano-VPOs, we have used this self-assembly of our VPO sources, structure directing agents. We end with fresh VPO, remove the template, obtain nano-VPO, and continue with physicochemical characterization. This is the proof that we have synthesized these hexagonal nanoporous materials. Basically, you have low reflections corresponding to planes 100 and 110 of these materials. So basically, this is an indication that we have obtained hexagonal nanoporous VPOs. TEM also has confirmed, transmission electron microscopy has confirmed the presence of these hexagonal arrays of nanopores. Size of these nanopores are around 4 nanometers, which is in completely agreement with XRD data. Now, after template removal, I'm showing here some XRD data, basically showing the the most intense reflection of for these materials after calcination, different samples, different vanadium and phosphorus sources. Here we have the spacing that corresponds more or less to these two theta angle reflections. So as you can see here, well, we have used different templates. This is the cationic template, the first approach I talk about. Fluoronics, it's a non-anionic template. So using both approaches is possible to retain the nano-VPO structure even after we remove the template. And I'm illustrating this idea here, comparing two XRD data for fresh nano-VPO and for calcined nano-VPO. So basically, we have the reflection here, so periodicity is not lost after template removal. So summarizing about the nano-VPO approach, we have synthesized VPO phases using both approaches, anionic approach and non-anionic approach. Elemental composition analysis has shown that again, this desirable PV ratio equals or close to 1, that is desirable for higher catalytic performance for the oxidation of N-butane. And it has been possible to obtain these thermally stable and single-phase nanoporous VPOs. General conclusions about this this work. Well, talking about macroporous VPOs, these materials, novel catalytic materials, has very interesting, remarkable, and unique characteristics. I have talked about them. We have obtained ordered 4 architectures in this range of 4 sizes, unprecedented high surface areas for this system, optimal surface composition for the oxidation of N-butane. Also, it's possible to have the catalytic active phase for N-butane oxidation, vanillin pyrophosphate, and it has been possible also to have preferential exposure of the selective surface planes. Talking about the nanoporous approach, well, we have presented 2 new synthetic pathways for the rational design of thermally nanoporous VPO materials with desirable surface composition, with desirable pore structure, for the oxidation of N-butane. So basically, these kind of materials, these novel macro and nanostructure materials, are expected to have very promising and interesting properties for the oxidation of lower alkanes. Just to finish this presentation, well, future directions of this work will include obviously further physicochemical characterization of these materials, catalytic tests that allow us to understand, to improve our understanding of the structure catalytic property relationships. And then the idea is to extend this proposed mechanism for the formation of other mixed metal oxides for the oxidation of other alkanes. And thank you very much for your time and attention. I'll be very happy to try to answer your questions.
Have we checked oxidation states of vanadium after calcination?
Basically, this is what we are going to do next. It's our next, talking about next physicochemical characterization. That's right, we need to know the oxidation states of our materials. Yeah.
So you talked about two different ways of removing the template, one with extraction and one with calcination. Do they give you different materials, and when you extract, can you extract all of that, all of the template, or do you leave some behind?
Well, the idea to extract with Soxhlet extraction is to have a more soft way to remove the spheres in this case. When you do calcination without Soxhlet extraction, it's difficult to preserve this hexagonal array. So the idea is to make this more soft way to remove the template to preserve the structure. Yeah.
So when you calcined, you had it collapsed to some extent.
In some extent, yeah, not the whole structure, but we have learned that it's better to do first Soxhlet extraction, and then you can do calcination.
Oh, so you're talking about sequential.
It can be both routes.
Okay.
I mean.
Okay, so when you extracted, do you have a feel for how much of that template you did remove with extraction? Is it 90%? 80%?
Basically, of course, you cannot remove all of them. Talking about percentage depends on the synthetic ratios, you know, precursor spheres ratio, but more or less, yeah, we're talking about 10% of or to 15% remaining of these spheres. Yeah.
What control do you have on the size of these you mentioned you have control. How thin can you go? How small can you go? And how does the structure stability depend on the thickness of the wall as you reduce the particles?
Yeah, this is a very good question. Talking about MACROPOROUS VPO approach, we can use different size of templates. For example, we have synthesized spheres in the order of 0.1 to 1 micron range, so it's possible to adjust the pore size. The wall thickness, it's a very important issue here. Some people have proposed that in order to have more thermally stable materials, you need to have very specific synthetic conditions, talking about mainly concentration of precursor around the spheres. The other case, NANOPOROUS approach, also it's possible to control the pore size. How? Well, basically there are two approaches. One of them is changing the nature of the template, the chain length of your template, and the other one is using expanders, such amines, such mesethylene, that almost double the size of the pore.
Also notice you have several different raw materials for vanadium. For example, you use vanadium oxysulfate, vanadium alkane. Can you tell us a little bit the effect of those raw materials to the formation of active vanadium pyrophosphate?
Well, basically, depending on the vanadium source, we are going to end with different catalytic phases. So we are now in the stage of exploring these vanadium sources and the effect on the final catalytic phase and their behavior in the self-assembly with our templates. Yeah. So,
which one is the best so far?
Okay, for the case of macro VPOs, let me see. Let me start first with NANO-VPO. For NANO-VPOs, we have obtained only single-phase materials using vanadium sulfate. With ACAC, we are getting other phases. We still see these reflections at very low 2 theta angles, but not single phase. In the case of macroporous VPO, we have used just vanadium 5 plus sources, which is vanadium pentoxide, and alkoxides, which are also vanadium 5 plus sources. So we have not explored the other sources.
I have a quick question. By measuring the crystal size in XRD, are the theoretical surface area in agreement with what you measured
Yeah.
by BET method?
Yeah, that's right. Basically, using this size of spheres and taking in consideration the size of our crystals, we are expecting surface areas in the range of 80 to 90 square meter per gram. So, as I show in one table, we're getting surface areas in the order as high as 75 square meter per gram. So basically, they are in a really short.